Welcome to another episode of XINABOX Daily. Today we're gonna talk about XINABOX and we're gonna look outside the box. So, what do I mean by outside the box? We have a concept we call walled garden. So you can see here, just over my head here, we have like this term walled garden, and there's like another term where they put it in brackets. And that's because in technology, when we talk about walled garden, we talk about whether a technology is open or closed. If the provider of the technology have kind of like walled it in and said, listen, you have to use all our stuff. We don't really want to mix with others. So from the same website from Wikipedia here, when you click on walled garden, it goes to something called closed platforms. And slightly down the slide here, there's like an example here from Harvard, where they kind of like compare some of the operating systems. So the walled garden is not only for operating systems, it's for all kind of technologies. So here you can see Linux is open, 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 and Apple iOS is open, close, close, close. And the thing is that the Linux operating system, the source code is open. You can go in and generate your own operating system by copying the source code and then changing it. And for that reason, all the software you develop, all the stuff you do in the Linux, your own program you run in Linux, everything can be open that way. In Windows, they are more open than some of the other, but they are close compared to Linux because the operating system, they don't share the source. But you can use any other tool to develop a Windows application. And you can run that on a lot of different computers. So it's kind of like open in a sense that they don't restrict how you develop software for Windows. Mac OS, on the other hand, do that. They have like an operating system, and when you want to make software for Mac OS, then you're enticed to kind of like go down the route with their software development platforms. And then it gets worse and worse. In Apple iOS, you have to, you can only install software on your phone that is on Apple's store. However, they allow other people to, develop software, so it's not only Apple software that can run on the phone, but it have to come from their store. And what's worse than the Apple iOS? Well, if you take like your TV, or a thermostat, that's a closed system. You can't change anything. You can maybe, operate the buttons or whatever it is, but you can't like make more apps to it or anything like that. So that's the concept of walled garden. So when we kind of like talk about, when I call this episode outside the box, I'm talking about how is it compared to being in, having stuff that is that where we integrate with the rest of the world.
Sorry,
Yeah.
I cannot see it. I can't see it broadcasting anywhere.
Okay. Hang on a second. No, it's live.
Sorry, I can't access it. I can't hear it.
So, sorry about that. So, on the so there's a couple of different concepts around whether the software or hardware is inside this walled garden or not. So what we have here is that we have a concept that's called open hardware. You can see there's like this logo here. If you go to open hardware on the Wikipedia, they have this open hardware logo. And it's very important to state we are not open hardware. We are not sharing our drawings of how we're doing our modules and things like that. I mean, it's not very difficult to figure out and reverse engineer it, but you can argue that with a lot of stuff that's out there. We are just not encouraging anybody else to do our style of hardware. The hardware is our breadwinner. This is what we're selling. It's not our final product because, we We also we also have libraries, we have software we put on top, we have lessons plan exercises, and our offering is much more than just our xChips. But the fundamental for what we do in the business is based on that we have the xChips. And when we many times invoice what we're doing, whether it's just xChips or software that runs on xChips or lesson plan and things like that, it's probably based on the pricing of the xChips that are coming out there. On the other hand, open software, so the term free and open source software called FOSS, that we are happy with. So we are, all our libraries, you can see all the source code. And one of the reasons for that is that we are not necessarily developing all our libraries from scratch. Many of the software we are developing is software that we have from like somebody else who done a library for a similar chip. We maybe modify it slightly, we give it some other names, all that kind of stuff. But the thing for me was that for us is that we are we encourage people to, of course, help developing software, because we want to sell the xChips and software and all the other material that's been built on top of that. We would like as many as possible doing that, because that will, of course, encourage selling the xChips. So therefore, we have this very free. Then, of course, another reason is that if you use our open source software, then there's a license that comes with that, and one of the paragraphs in that license many times are that you have to keep on have it as open source. There's some license they allow that you can just include it, and maybe you just have to refer to people inside your code, but you don't have to otherwise share it. And there's a few apps that we haven't shared, and then more because they're a little messy inside, so we don't want to share them and then have to explain how the whole thing works before we can kind of like share them properly. So that's the open software. So our hardware is closed, our software is in general open. Now we are actively open, and I'm going to use this picture here on the screen to give an example of what I mean by that. So the BS01 Bridge and SS Single Board Computer 1, that is the PC104 interface, and that is the one that works on most computers in the world, because the PC104 is one of the oldest single board computer standards. They're very expensive, so there's not necessarily as many of each of them, but there's many different of them. There's a bigger variation of single board computers here. There's just not many of each of them, because they are, they can be $500 to $1,000 each. But because of that expensiveness of these, then we have also not necessarily gone down and built this connector as the first one. So this one right now we only built to order, while all the other ones you see on the screen is available on our store. The 96 boards is a newer standard, much newer compared to the PC104. And that standard is kind of like want to take over where the PC104 left, because it has so many pins. It's like a very bulky. The the 96 board standard, it's much more simple, and there's a lot of boards that's built for that. So our B901 can be used for all the boards that runs this B96 board standard. Then of course there's a Raspberry Pi. There's 35 million of these Raspberry Pi sold. So the BR01 is of course there because there's so many Raspberry Pi. But because there's so many Raspberry Pis, there's a lot of other single board computers that decided to use the same kind of like connection. So our BR01 works on all the computers, our single board computers. They uses the same Raspberry Pi interface. So they're of course the more or less direct clones, the Orange Pi, the Nano Pi, the Banana Pi, all those. But there's also other computers that doesn't try to be a necessary clone to Raspberry Pi, but that just use the same interface because that works and people have learned to kind of like accept it. Now in the US, the BeagleBone is a favorite, especially in universities. Most university satellites that have been set up that have to use a computer, they will prefer to use the BeagleBone. It's said to be a more robust, a single board computer. So therefore, they're using that one. And of course, we interface that to that one also. We have the microbit that you're familiar with. Everybody in grade 7 a couple of years ago received one in the United Kingdom. So therefore, there's a lot of these, millions of these microbits out there. So we've done several interfaces to that. Our latest is the IM01 that also give SD card interface. And just to kind of like explain the openness here, Pixhawk is a is a computer that used on most drones out there where the drones have been developed. So it's professional drones, and we've done like this little interface here that allows us to connect other xChips to the Pixhawk. There's like an I2C interface. So we simply just done an I2C interface there, so you can take like our weather sensor, connect it there, and when the drone flies around, it can gather data like that. Because it's so well used, it's also used in not necessarily stuff that fly, but sails or drive or other unmanned or drone style stuff of different types. So this is what I mean by actively open. Unlike, for example, here's Littlebit. They are selling these connectors, these gray connectors here that allow you to then, build a board that you can integrate with. But they haven't done like a Raspberry Pi board or like a BeagleBone board or any of these boards with this connector on. They like, hey, if you want to connect these things here to Raspberry Pi, well, you have to build your board yourself and like this thing here. So it's kind of like who is reaching out to who here. We are reaching out to the world by doing interfaces everywhere because we think it's in our interest to have it that way. Because yes, if people have a Raspberry Pi and I want to, just use our sensors, we don't have to necessarily do all the software and lesson plan and things like that. People will just buy our xChips, and that will be easy for us. So that's the reason why we will reach out to all the different single board computers and all the different other equipment that exist out there, so we can just sell a lot of sensors. So when we have to, when we kind of like have interface like similar here to Littlebit, the problem was that we needed to actually build a computer module because Littlebit doesn't have really a computer module in there. So the ILO1 was the interface Littlebit. It has a little CPU on the back, and we decided to not pursue this thing here right now because the Littlebit have a complete different market. It's like very much more toy, and going down the line with what we have already with all the sensors we have and things like that, it wasn't like the right way of going. So if you want to now go outside the box, what is it then that you have to look for? How do I get from XINABOX style work and then look for what do I look for on our xChips in order for me to kind of like go outside the box and speak the language that speak outside XINABOX? So what you have to do is you go to our website, you go to our component, and you look in the brackets. So here's the CW1. In the brackets, it say ESP8266. Now, the next three numbers here, ESP8266 being one of them, and the two next is kind of like what the rest of the presentation is going to be about. So this is the ESP8266. So there's other component on the CW1. You can see there's a RGB LED, and there's like a couple of other passive components. But the main component is the ESP8266. And this is a very, very, very famous Wi-Fi chip. There are a lot of different developers that have been using that. A lot of people that do it yourself using this one. So that's the reason why this was our first Wi-Fi chip, because it's simply just that famous. The company who makes that have made a new one called ESP32. So that was our second one, CW2. So these two chips are now some of the leading chips in embedded Wi-Fi computer chips that's out there. And therefore, they can be used a lot of places. And that's what we try to do, is we try to not come up with some exotic chips that is not being used in general and only we using it. No, most of our sensors and most of our cores are well-known cores out there, so you can easily take another system and incorporate them. Because we're also happy that you don't program in MakeCode or Python, but program in something completely different, which the rest of this presentation is going to show. Now, it's not only like that for cores, it's also like that for our sensors. So here is a SW1. The main chip that sits on SW1 is called BME280. The BME280 is probably the most well-known weather sensor chip that's out there. It's very accurate, and it's been used really a lot of places. There's almost always a driver for the BME280. So I want to give some examples, as you can see here, of where I have looked for this thing here to kind of like go outside the box. So one of the examples I haven't put in here because I presented that earlier was like Sirens. So Sirens have kind of like included us. So we now called CW2 in Sirens. But before we talked to them, then was ESP32. Also, our libraries we have at Sirens is now called SW1 for the BME280. Before we kind of like got included into Sirens, it was a BME280. Didn't stop us from actually develop there using our CW2 BME280, but we kind of like now got name recognition there, and I kind of like made sure that there was helps online on their website so they can see exactly how we use it. The examples I'm giving here today are all kind of like outside the familiarity with what we normally see and program in. So the first one here is a company called Atmosphere IoT. One of the reasons why I like these guys is that they're web-based. They have this drag and drop style programming. Little like MakeCode, but this is like really, more like the professional level IoT. So what you do here is that you drag and drop this thing here. You build actually an app on your phone with this, or you can even upload stuff to the cloud. I think they support Amazon mainly. And when you program it, you have like a little agent, they call it, that runs on your computer in the background, and the browser then talks to this agent to your core, and it puts the code in that way. So they have like a lot of sensors, but the sensors are called BME280 and not SW1. And the cores are not being called CW2 because they don't know about us. But that doesn't mean that you can't use the system and program our stuff there. So when you want to create a new project that comes out and say, what kind of core do you want to use? They of course call it something else than core. They call it maybe a board or chip or whatever it is. And what I have done is I highlighted this big box here. You can see it says ESP32 all the way down. So this is our CW2. So our CW2 is supported here directly. And the thing is that the two top ones is from Espressif directly. So this is kind of like the barebone ESP32. That will work with ours because ours is like a barebone just put on a white PCB. But you can see there's also a named version. So there's like this M5 stack from M5 stack, and wouldn't it be nice that we have like maybe something called CW2 and in a column of the provider it says XINABOX. So what we're doing is that we're constantly going out there and integrating our stuff and getting this name recognition different places. Now, we have been contacting Atmosphere IoT, but they've gone through like a merger and acquisition or something like that. So they have had like a longer pause. So we are kind of like giving them a little bit of space until they found their feet again. The small box up here is just to show that there's of course a lot of other cores, but that specific one is interesting for us because later this year we're coming out with a new core called CBO3, which is based on that specific chip. And one of the reasons for that is that it's a very low power and it's Bluetooth. It also have a lot of other communication standard. It doesn't have Wi-Fi because that will be too much power. But it's a very concentrated little chip and it's going to be much easier to program and interface with. So it falls in like very nicely between our Wi-Fi chips. They're a little bit difficult because you have to configure them Wi-Fi style, and our other chip that doesn't really have a communication standard. So they're also supported here, and that's supported many other places. Then there's Mongoose. Now, when I started the XINABOX, a number of years ago, Mongoose was one of the first one I kind of like had my eyes on, because they support both the ESP32 and the ESP8266, with other words, both the CW2 and the CW01. They also support some chips from STM and other from TI, but of course the ones we're interested in is the last column here. So we could also do Wi-Fi chip with the other one, but why bother if the ones we have there is supported already? So Mongoose allows you to program in C, but even better, you can program in JavaScript. Now, when you program in JavaScript or C, and we kind of like go out and say, well, the CW2 or CW1, you can program in a lot of different languages. The right way of kind of like thinking about it is that there's a lot of IDE, integrated development environments. So Arduino is an IDE, Mongo is an IDE, Atmosphere IoT is an IDE. But underlying is that underneath Arduino is C programming. Underneath Mongoose is JavaScript and C. Underneath Atmosphere IoT is this drag and drop, and there's even a level lower there that I believe is JavaScript. I can't remember, but there's like some manual coding you can also do there. MakeCode is kind of like an IDE. You can drag and drop, but you can also shift to JavaScript and Python inside MakeCode. So think about these different environments as IDEs, and what you have to figure out is that have they made support for your core? And they're not going to say CW1 or CW2 necessarily, so you have to look for ESP32 or ESP8266, or what name we have on our other cores. And that's, of course, if you want to program our cores with that, because there's a lot of systems that program, let's say, the Raspberry Pi, the PC104, the BeagleBone, and things like that. And all of those, there you just have to have the support for a library support for our sensor. Lua. So here is a programming language that's called Lua. And that was originally developed for embedded programming, for the stuff that we do here with Internet of Things. So it's a very strong language there. There's a lot of benefits from this thing here. And NodeMCU here is an implementation of Lua on the CW1. So you can program your CW1 in Lua with this thing here. So now we can say, tick, you can also do Lua on our environment. Now, if you program in Lua, you need like a IDE. So Lua is and NodeMCU is kind of like spread a little bit. So there's another company that made an editor here that allows you then to program in this Lua. It's a little like MicroPython. Yeah, it's great, but how do I edit it? And therefore we have Mu editor. The same as CircuitPython. In Arduino we have that editor that's there to program Arduino, which is C++. In MakeCode, we have a web-based editor that allows us to program that. So you need the editor, you need the entire interactive development environment to do that. So when it comes to Lua, they didn't have anything. They just had like little MicroPython, the stuff you loaded up to your chip, and then somebody else, like with Python Mu editor, or with Lua, the ESP Explorer here, Explorer, is then the IDE for that. When you want to put Lua on your CW1, you have to build a firmware you put on it. When we program in MicroPython, that firmware you put on the CW1 or CW2, you do that via XINABOX uploader, because we have done a support for MicroPython. So we've taken the MicroPython and put it into XINABOX uploader, and you then can upload it. You don't have to go that way. You could actually download that file yourself and upload it to our CW and CW2 and CW1 the way the Expressive normally do it. But that's very not user-friendly, let's put it that way. So, with Lua here, it might be that we want to do, a pre-built Lua platform that we then put into our XINABOX uploader. So if people want to program Lua, they can simply upload it that way. That's for time to decide, because that will be another platform. We might not want to support many different platforms, but just support the platform we do much better. I put an arrow here on BME 280 because that's a SW1. So the way Lua works is that you have to tell what libraries you want to use up front. So you build your firmware with all the libraries, and then when you start programming, they're already there. In MicroPython, as I showed the other day, you simply just take and drag the library for that sensor you want to use in. So it's not part of MicroPython that way. So the last couple of things I want to show is that if you want to like really see what the expense is of our system here, then on our website there is a number of different blogs. Here's one from October 2018 where I show how to use PowerShell, which is another kind of like programming facility that comes from Microsoft. And I'm actually have the SW1 there programmed on a Raspberry Pi using PowerShell. So PowerShell runs not on the CW1 and CW2, but it runs on the Raspberry Pi. However, I needed to make sure in PowerShell that I could access one of our xChips. So there they will refer to BME 280, not to SW1. So, and the same with the display here, the ODO1 was referred to in a PowerShell with its SSD 1306 name. Another place to go, so that was the Microsoft PowerShell. Another place to go is on our YouTube channel. Here is a video I made, and it's on our YouTube channel, how I communicated with Raspberry Pi using a built-in language. So when you install the full version of Raspbian on your Raspberry Pi, you get something called Wolfram Mathematica. So I thought, well, if that's there as something that's pre-installed on the full version of the Raspbian software, maybe I should actually try to use this programming language and see if I can interface to our xChips. Now, unfortunately, there's no like library system here, because the whole idea with Wolfram Mathematica is more that you put models together and things like that. But hey, we're in the business of putting live data in, and Wolfram Mathematica do actually have an I2C interface. So what I did was that I wrote the code to interface to our xChip directly, so there's no library in between. Now that's not easy, but the SW10 is by far the easiest chip to interface. So typically when we start a new implementation, so for example, the first chip we implemented when it came to Python or to Sirens is the SW10. It's very, very easy to get it to work, and you get the temperature out there from this very, very easy. So the program example here is how I interfaced to I2C directly. And it might be interesting if you kind of like have another system that you want to work with, and there's no like library support for any of our xChips, but you want to try to see if you can get it to work. This example is a good way to see how do you get I2C to work. There's a lot of other examples how to get I2C to work, not from us, but on YouTube in general. So I urge you to go there and look. But as I said, our website and our YouTube channel is full of examples. Of course, the Hackster have examples, and we always try to do something a little bit outside the box to kind of like the further we get outside the box, the more likely we run into other people that's out there that will meet us halfway, because we can show them how to work in PowerShell. If PowerShell is their dream, well, there you have it. Now you can actually use our xChips with PowerShell, and we reached out to a lot of people there. So what we try to do is that find these different solutions, make example for this thing, and say ours work there also. It's maybe not called CW2 and SW1. It may be called ESP32 and BME 280, but you can still use it. You don't have to have necessarily our libraries and our naming to do that. So that's it for me.